So now focusing on cyclohexane, there's that chair conformation. And there is a pretty little model of it. And what I want you to notice, I've tried to color code again. So we got the grey carbon up the back going to purple and blue ones, which then goes to a black one, then to a red one that's sort of down the bottom of the chair. That's where your feet would go, and then the yellow, and then the blue back again. Okay. If we actually look down at cyclohexane from the top, so there's the picture of it. It's a nice little alternating up-down ring. There's the silver is up, then the blue and the purple are down. Then you go up to the yellow, up to the black, and then down to the red again. So this ring is actually nicely nestled on this tabletop, so that the blue, the purple, and the red are sitting on the tabletop, and the grey, the yellow, and the black are above the tabletop. So it's a nice puckered ring as well. So again, you could kind of, if you twist your head on this one, you can see up, down, up, down, up, down. Now, I said I wasn't going to be too worried about conformations and weird stuff associated with cyclohexane, but it is time to introduce a little bit of terminology. If I draw out the ring, that's the nice chair, although again emphasizing the up, down, up, down, up, down. You can see each carbon, of course, has two hydrogens on it, but they're in a very distinctive pattern. Each carbon has got a hydrogen that's essentially either pointing straight up or straight down. These are known as the axial hydrogens. Okay, and then each carbon's got a hydrogen that, while not flat, is certainly not pointing down. It's sort of pointing directly away from the ring, and then either down a little bit here or up a little bit there. These are called equatorial positions. So each carbon has an axial hydrogen and an equatorial hydrogen, or generally I should say an axial bonding position and an equatorial bonding position, and they alternate as you go around. So the up carbons, like the grey one, the black one, and this orange one, the axials are pointing up. The down carbons, like the purple, the red, and the blue here, the axials are pointing down below the ring. Okay, and the equatorials alternate in the other direction. So the up carbons, the top carbons that had the axials going up, have an equatorial pointing slightly down below the ring, whereas the next carbons, the down carbons, the purple, the blue, and the hydrogens, and the purple, the blue, and the red carbons, they're equatorial ones pointing slightly up above the ring. Okay, so you've got axial positions, equatorial positions. You also have to think, are we above the ring? Are we below the ring? Hopefully that picture is not too busy and it kind of makes sense to you. Now we're going to apply that, could spend hours on these cyclohexanes, and as I said, there is an extension topic that will spend not hours but certainly more minutes on it. But the last thing I want to do is just consider these dimethyl cyclohexanes. So that's a cyclohexane ring that has two methyl groups attached to it. And as you can imagine, there are various structural isomers possible. For example, we could have this one here, where both methyl groups are attached to the same carbon of the ring. This would be called 1,1-dimethyl cyclohexane. And so here it is, just the regular skeletal structure, not quite skeletal structure because I've sort of spelled out that those are CH3s, but you know what I mean. Here's one showing the nice little chair conformation. There's one of the methyl groups in the axial bonding, one of the methyl groups in the equatorial. And here are pretty little models of it showing here's the ring, above the ring, in this case the axial, below the ring, in this case the equatorial. And you can see it a little bit better from the flat view there, the yellow coming out at you, the red going away from you, just to hopefully allow you to appreciate a bit more the axial and equatorial positions. Okay, well that's one structural isomer, but now surely we can get another one by just moving one of the methyl groups to the next carbon. So that would be, of course, 1,2-dimethyl cyclohexane. But when we look at this in 3 dimensions, we actually see something rather interesting. We could have this particular structure here in which you've got the methyl group on carbon 1, which I'm drawing as my yellow methyl group, is on the top of the ring, and then the methyl group on the purple carbon is also on the top of the ring. This one here I've drawn as axial, this one is equatorial. They're both on the top of the ring side. Okay, now compare that to this picture, in which again I've got the CH3 on top on carbon 1, but now the red CH3, the red ball, is on the bottom of the ring. So in this case we got an axial and an equatorial, and in this case we got an axial and an axial. These are different molecules. Okay, one of them is where both methyl groups are on the same side, one is where they are on opposite sides. These are not different conformations. You cannot, by just rotating the molecule, rotating bonds, flexing a little bit, you cannot turn one of these into the other one. You would have to break bonds in order to turn the compound in which both are on the same side to one in which one is on one side and one is on opposite sides. These are isomers because they've got the same formula, but they're not structural isomers because they have the same connectivity. They're both 1,2 dimethyl cyclohexanes, but they're different molecules. They're not different conformations, they're different isomers. They are examples of geometric isomers. This is a type of stereo isomerism. Same formula, same connectivity, different arrangement in space. Okay, we saw the first type of geometric isomer with enantiomers. Now we're seeing these geometric isomers, which are known as cis or trans. Cis when both methyl groups are on the same side, trans when they are on opposite sides. So you've got structural isomers, 1,1-dimethyl cyclohexane, just the one isomer. 1,2-dimethyl cyclohexane, however, you can have both methyl groups on the same side of the ring or on opposite sides of the ring, thus it has two geometric isomers. Let's continue with 1,3-dimethyl cyclohexane. Okay, that is a structural isomer from the 1,1 and the 1,2, but it too has two geometric isomers. Here's the one where both of the methyl groups are on the same side of the ring, so they're both on top of the ring in this case, so that's cis 1,3-dimethyl cyclohexane. And then here we've got the yellow one is on top and the red one is on the other side of the ring, above the ring, below the ring, trans. Okay, and then wrapping up with 1,4-dimethyl cyclohexane. Again, we can have two geometric isomers. This one here, where both are on the same side of the ring, we've got a axial there and an equatorial there, but they're on the same side of the ring. And then the other possibility, the trans 1,4-dimethyl cyclohexane, where one is above and one is below. And you can see that, I think, really well with this particular picture. So we didn't need to do much on cyclohexanes. I don't think you do, cis, trans, isomers with regard to cyclohexanes, but it's a useful way to start emphasizing the different type of isomers. Structural isomers, we have 1,1, 1,2, 1,3 and 1,4 dimethyl cyclohexane, 4 structural isomers. However, there are a total of 7 geometric isomers where you've got the same formula, the same connectivity, but different arrangements in space. Hopefully that made sense. Done with the organic topics, the main organic topics for this week. Next week in the organic string, we will be moving into alkenes. Looking forward to that very much.